Okay, so thanks, Justin. Like Aditya and Justin both said, I'll be presenting on the asynchronous distributed memory task parallel 3D unstructured mesh data transfer we're working on in Quinoa. So this has been work with Joseph at Los Alamos National Laboratory, and then from Charmworks, Eric Boehm is the PI on the project, and then myself and Nitin Bhatt. So we just heard about quinoa. I don't really need to go over too much of it again. Just as a short slide, just reminding you it's a project from Los Alamos. It's a CFD application developed for Charm++, open source, and this work is part of the phase 1 SBR, which started in February 2020 to further develop quinoa in conjunction with Charmworks. And so the long-term goal, which by this point is probably more of a short-term goal that I'll be touching on in this presentation, is combining the CFD with structural mechanics by using parallel collision detection to do mesh-to-mesh data transfer. And this work is still in the fairly early on stages. Unfortunately, we're just now getting to the point where we're beginning to look at performance. So this presentation will be plot-free, but we'll give you an idea of sort of where we started and where this project is going. So like I mentioned, we're working on using collision detection to do scalable parallel mesh-to-mesh transfer. We're developing a library that right now we're calling EXA-M2M, which is a library for performing mesh-to-mesh transfers on unstructured meshes. The sequential algorithm was originally developed by Joseph, and now we're working on the parallel implementation as a collaborative effort between Joseph and Charmworks. And the crux of the library, the kind of the centerpiece of the library, is utilizing the existing collision detection library that was developed for Charm++, I think in around 2006. And so I'll be talking a lot about that collision detection library today. But the basic algorithm for the mesh-to-mesh transfer is fairly straightforward, broken up here into 5 steps. Basically, for the first step, you're just setting up the mesh data. Right now, it's just a standalone Charm application. We haven't converted it to a library yet, so we're just reading meshes from file and partitioning them Zoltan. But part of developing the library API will be allowing the application to actually transfer the mesh data in. Either way, the mesh data is stored in a worker char array. So again, it's going to be virtualized across processes. There's going to be many worker chars per process, all holding their own chunk of the mesh. And they're going to be sort of the workhorse for the library. The second step, which is the big step, is we pass this mesh data into the Charm++ collision detection library. And so here the source of the transfer is going to submit a list of bounding boxes for each tetrahedron in its mesh, and the destination of the transfer is going to submit bounding boxes for its vertices. In this case, at least right now, 1 vertice per bounding box. Chunking that up differently is something we can look at in the future, but right now it's 1 vertice per bounding box and 1 tetrahedron per bounding box. And just to clarify what I mean here in case I forgot, the source mesh in this case is the mesh where we have the solution at all the vertices, and we want to figure out how to kind of overlay the destination mesh on it, how it intersects with the source mesh, and then interpolate the solution data from the source mesh to the points of the destination mesh. So this collision detection library is going to do collision detection and return us a list of potential collisions. I'll explain on the next couple slides why these collisions are just potential collisions. But once we have this list of collisions, they'll be distributed back to the destination mesh for further processing. The destination mesh splits up these collisions based on the source mesh chars that contain the relevant tetrahedrons and sends it to the source mesh. And then the source mesh does the actual collision detection with the tetrahedrons and interpolates the solutions to the different destination points. So like I said, the step 2 is sort of the crux of the algorithm, and that's where the majority of the work is going to be done. And so that's what I'm going to look at in a bit more detail here. So for the collision detection in EXA-M2M, it's using a 2-phase collision detection. Phase 1 is what we call the broad phase, and then phase 2 is what we call the narrow phase. So in the broad phase, we're just doing basically the quickest, dirtiest collision detection we can think of, which is just colliding bounding boxes. Determining whether two bounding boxes collide is very quick and cheap to compute. It's also a very general case. So this is what's handled by the Charm++ collision detection library. We pass it a list of bounding boxes, and it determines where potential collisions may lie. So in this small picture below, we see that the trapezoid potentially collides with a triangle. The circle potentially collides with a triangle. Obviously, we can see that it doesn't, but their bounding boxes intersect. So the library determines that's a potential collision. But then the star we can rule out because its bounding box does not intersect any of the other bounding boxes. So in the narrow phase, that's where we take this list of potential collisions and do the sort of application-specific collision detection logic in response to the collisions that we detect, et cetera. So this generally is going to involve probably more expensive collision detection, but because we do this two-phase approach, we have far, far fewer collisions to check because the bulk of the work and the bulk of the paring down this list of objects to collide has been done in the broad phase. So that's where in this small example, the application would detect that, yes, the circle does not in fact collide with the other two shapes. So the broad phase, again, handled by the collision detection library. Like I said, I think it was written in 2006-ish. And it's detecting collisions or intersections between objects scattered across processes. So it's completely distributed. It has applications in computer graphics and animation, computational physics, robotics, etc. And like I mentioned, in our case, what we're colliding is the tetrahedrons of our source mesh with the vertices of the destination mesh to find out essentially which solution points need to be interpolated to the vertices of the destination mesh. So the collision detection library kind of works in three large steps. It's based on the idea of voxels. So a voxel is just a 3D cell in a regular axis-aligned sparse grid, or really in any dimensional cell. In the library's case, it's 3 dimensions. In the example on the right, we see a 2-dimensional example, but it's generalizable to any dimensionality. And one of the important parts here is that it's a sparse grid of voxels. So step 1 is we're populating the voxels by telling it what the objects are that we're actually trying to collide. So in the case on the right, we see there's a hole in the middle because there are no objects that intersect with that voxel, so we don't need to concern ourselves with that voxel. And so this is implemented using a char array. Each element in the char array is a voxel. The char array initially starts off empty, and step 1 is the application passes in lists of bounding boxes, and using demand creation in Charm++, these voxels then come into existence. And so for those unfamiliar with demand creation, that's a special feature you can use for char arrays, where instead of actually doing bulk insertion when you create the array or doing regular dynamic insertion after you've created the array proxy, you can actually just start with, for example, an empty array. And as you call entry methods on array elements, the distributed location manager will determine, does this element that you're trying to send this message to already exist? If it does, reroute the message as normal. If it doesn't, first create the object and then deliver the message. So in this case, as we're adding objects, they'll be created as the first objects get added. And then once more objects are getting added to voxels from, for example, other processors, they'll be routed to the correct voxel. The other thing to notice is that, for example, with the larger circle in the bottom middle, that intersects, in this case, 4 voxels. So each voxel needs to know about any objects it intersects. So those 4 voxels will all know about that circle to do potential collision detection. So step 2, once we have our voxels populated, we just run a serial collision detection algorithm per voxel just to collide the pairs of bounding boxes that the voxel knows about. This is pretty straightforward. So in the example on the right, we see there's a bunch of voxels that only have one object. Those don't matter. But then I've narrowed it down to just these 3 voxels, which have potential collisions. They're going to run collision detection on their list of objects. And in doing so, we'll determine that there's a potential collision between the triangles in the top left, the triangles in the middle right, but the circles don't collide. And then these voxels all just do a big reduction to concatenate this global list of possible collisions and return it to the caller for further processing. Um, so that's the broad phase of the collision detection. What do we do in XMTEM to further process these collisions? So like I said, this is where, again, we're dealing with tetrahedrons and vertices, or in the example on the right, triangles and vertices, but it's the same general principle. Here we need to find out which of these vertices actually collide with which actual tetrahedrons, and then we can interpolate the solutions. So we distribute the collisions back to the destination mesh because that's who has the information about the vertices. So each destination mesh will then distribute its own vertices to the source mesh chars that they are potentially colliding with. One thing to note is that there may be multiple potential collisions per source char. So for example, the vertices I've circled on the right, when you're doing just bounding box collision detection, those actually will potentially collide with multiple tetrahedrons, or in this case, the triangles. So what we get back from the collision detection library are multiple collisions dealing with these vertices. So we'll be sending multiple potential collisions to the source chars. But then once the source chars get this information, then we can actually determine what the actual collisions are. And then once we determine the actual collisions, we can interpolate the solution to the vertices based on the vertices of the source tetrahedrons that we're actually colliding with. And at that point, we have our solutions for all of the destination points, and we've accomplished our goal. So like I mentioned at the beginning, we're just now getting to the point where we're going to start looking at performance. So I don't have any cool or interesting plots, but we have gotten initial results on correctness. So we're pretty confident that things are working as expected. We started with some sequential verification and some multi-core verification, scaled up to multiple nodes, increased the amount of virtualization. And so this was a run that Joseph did on just doing a simple transfer between a sphere and a cube. We had two 48 million cell meshes run on 216 cores, 5 compute nodes. I'm not actually sure what machine Joseph ran on, but that was the basic setup. And the right is just showing what's actually 2 lines showing the actual solution and the expected solution, and they overlap exactly. So like I said, now we're at the point where we're going to start looking at how this performs, how it scales, and integrating it into Quinoa. So potential future directions, first and foremost, tune and analyze our scaling experiments. We currently have a lot of potential knobs to tune, the degree of virtualization, the voxel size we give to the collision detection library, different partitioning schemes, etc. The next thing is obviously then to also develop a library interface. So the worker char arrays within the library are going to be bound to char arrays in the calling application so that the data transfer does not require messaging. We can just hand over pointers to the mesh data, have the collision detection library, or sorry, the XMTM library run and automatically interpolate the solution without having to send any more messages between the library and the application. And then we want to integrate it into Quinoa, and that's kind of the big milestone we want to reach within the next month or so, integrating into Quinoa so that in each iteration of Quinoa, we can call this XMTM library and do some mesh-to-mesh transfers. We're also looking at some improvements to the collision detection library. Like I said, it's pretty old, so one thing we want to do is modernize the API a little bit, and in doing so, we want to make the post-processing of collisions more easily distributed. Like I said, right now, at the end of the collision detection library, all of the collisions are gathered up in one giant reduction and concatenated into one big list on processor 0. First of all, that's not even customizable where the giant list goes. And second of all, it's a giant list of potentially millions of collisions. So we suspect that might be a bottleneck in processing. We want to improve the API so that the actual collisions can be automatically returned to the whatever parties are concerned with those particular collisions. In this case, they should be returned right back to the destination mesh. And in doing so, we want to make sure that we can map things accordingly so we can reduce the cost of communication there, et cetera. We also, in the current scheme, our mesh is partitioned, and of course, we're going to have vertices shared on boundaries between chars in the destination mesh. Right now, every char submits all of its vertices, which means we have some duplicate collision detection going on in the library. We want to weed that out and make sure we have a scheme to correctly balance that. Again, tuning our voxel configuration, and then probably also in general some more efficient collectives for post-processing that shows up as a particular performance problem when we're doing all this large, basically all-to-all between the destination and source meshes at the end of the computation. But yeah, that's my presentation on sort of the start of this project. So if anyone has any questions, let me know.
Well, I guess I will ask a question to get started. Not a question so much as a musing, because I hope I noticed some of the former students are here. I don't think Orion is joined here. If he were, he could answer this question. Orion Lawler is the original author of this library. The claim to fame of this library is that it is highly distributed, highly scalable, asynchronous, mainly asynchronous. And so I'm a bit surprised at the fact that the list is being returned to one place. I suspect that this is because the original thing was for collisions between two meshes, which happen in a very few points. Not in mesh-to-mesh transfer, it happens everywhere. Whereas if we just have some kind of a finite element structural dynamics code, where in a crash-like situation, the mesh normally doesn't bump into itself, and where it, on a few points it bumps, you're creating this list to send back. So that may be the reason why it doesn't show up this problem. But the library is meant to be highly scalable, and we would like to restore that it to that by returning the results to the clients. It says, I was looking at the paper while you were talking about it. So it should be returned to the clients rather than collected centrally. I don't know if that's more a comment than a question, but do you have any thoughts on that?
Well, yeah, so yeah, like I said, the whole thing is meant to be distributed, and it is weird because the majority of it is very distributed and asynchronous. It's just that very last step. And the one thing that is also sort of promising is that because of the demand creation and how that's set up, as you're contributing objects and these voxels are being created, there's also a decent chance, based on just the locality, that when a client adds its bounding boxes in the library, the voxel or the voxels that's responsible for those objects, if your mesh is also partitioned with some locality in mind, those are probably going to be co-located with the clients as well. Especially if we have, for example, the destination mesh contribute its bounding boxes before the source mesh does. So not only will we avoid that bottleneck of gathering this big list in one centralized location, there probably won't be that much communication in returning the data to the clients as it is anyways, because in a lot of cases, the data will already be co-located on the same PE.
That would require a round of load balancing, I assume.
So again, it depends. Actually, mostly I think it depends on how the data is originally mapped to the chars. Because of the demand creation, if I have some particular set of vertices and I'm the first person to contribute those, or when I contribute those, if I'm the first person that's contributing something for that particular voxel, the demand creation will have that voxel created on the same PE as me, as I am. So in a lot of cases, the owner of these vertices bounding boxes will be co-located with the, or in at least as many cases as possible, will be located with the chars that contributed the vertices to begin with. So once we have that list of collisions with those vertices, returning it to that client won't involve messaging in a lot of cases.
Nice.
And I do think then that will also, again, add emphasis to make sure that we have a good partitioning of the mesh in the first place.